SwayamPrabha. Digital India. Educated India.
Hello everyone. So let's continue from where we had left off. We were talking about the scales of turbulent motion, right? We were talking about the model spectra in the last class. And here I just want to go over this particular figure one more time. And because we had to do this towards the end of last class. And I just want to finish this up. So what is shown here is the model spectra of the 1D spectra, okay? And I want to point out that on the y-axis, we have a scaled longitudinal velocity spectra. So that's the 1D, and so it is a longitudinal velocity spectra. And what it is scaled appropriately in such a way that it is divided by epsilon nu to the fifth to the 1/4, which is what is shown here, right? Now, why is it scaled with epsilon nu to the fifth? That's because we saw this earlier. It actually arrives purely because of dimensional analysis. The spectra is scaled to be non-dimensional. And you will see that if you go back a few slides, you will see this expression where we had the spectra. In order to non-dimensionalize it, we multiply it with epsilon nu to the fifth to the 1/4. Epsilon is the dissipation rate, nu is the kinematic viscosity. So we were using epsilon and nu in order to non-dimensionalize it. That's it. The idea was, because you have two ranges, right? The energy containing range and the universal equilibrium range. And according to the Kolmogorov's hypothesis, the universal equilibrium range depended on both epsilon and nu. So if we found a way to use those two variables, epsilon and nu, to non-dimensionalize the energy spectra, maybe we could write it in such a way that it is non-dimensional. So that is what we are doing here. So you have EK, E of kappa, is epsilon nu to the fifth to the 1/4, and then this universal non-dimensional function, which is psi kappa eta, which is a Kolmogorov spectrum function. That's what we started with, right, in this whole exercise. Now, here, what we are doing in this figure is that, I'm going back here, we are dividing it on the y-axis. The energy spectra is divided by this particular expression, epsilon nu to the fifth to the 1/4. So then it becomes non-dimensional. Now, not just non-dimensional, we are scaling it with the right parameters in such a way that, because the universal equilibrium range only depends on epsilon and nu, you would think that if you scale it with that expression which makes the energy spectrum non-dimensional, as in epsilon nu to the fifth to the 1/4, the whole thing to the 1/4, then the universal equilibrium range will actually look universal in the energy spectra. All the spectra will in fact overlap, and that is essentially what we are seeing here, right? And this is what I wanted to emphasize again starting in this class. So we have the energy spectra shown here in this figure, energy spectra scaled, and it's 1D by the way, and on the y-axis. On the x-axis, we have again scaled the wave number with the Kolmogorov scale. Why are we scaling it with the Kolmogorov scale? Because we want to look at the universal equilibrium range, not the energy containing range. We want to look at the universal equilibrium range, and that's what we are doing here. As you can see, there are multiple data sets in here, and all of this, right, are different data sets. All of this is different data sets. So some of them are grid turbulence, some of them are channel flows, some of them are boundary layer flows, and there are different Reynolds numbers in here. Okay, there are different Reynolds numbers in here. In spite of that, you see all the data sort of overlapping as you go to higher kappa eta. So you have the inertial subrange here, which you would think is a minus 5/3 slope. Then you have the dissipation range here, which is past the inertial subrange, and both the inertial subrange and the dissipation range together, which make up the universal equilibrium range, overlaps. That's the beauty of the way we have plotted this energy spectrum. Now, the energy containing range is this part here, this circled part here. And obviously, it is going to be different for different kinds of flows because you have different Reynolds number data in here. And you would think that the higher the Reynolds number, the higher are those energy levels, because higher the Reynolds number, more energy you have in the large scales. Right? More energy is produced due to turbulence, due to the higher Reynolds number. So accordingly, the levels of this energy in the different data sets will keep increasing with increase in Reynolds number. Now, it is not just symbols you see in this figure. There are also lines. Those lines are the model spectra that we discussed in the last class. Model spectra according to the different Reynolds numbers. You can have a model spectra which is governed, whose behavior is governed by the Reynolds number. Now, it has mainly two functions. A function that shows the energy containing range, right? The FL, if you will, and then the F eta, which was the function for the dissipation range. So this is what you had. If you remember, this is your model spectrum shown here. This here, epsilon to the 2/3, kappa to the minus 5/3, is for the inertial subrange. This is for the energy containing range, and this is for the dissipation range. So you have three functions for three different ranges in your energy spectra. That's essentially what you're doing, isn't it? And that model spectra is built according to the Reynolds number that you have. And as you can see, the model spectra matches the data, the experimental data, extremely well. Extremely well. It matches it extremely well at the different Reynolds numbers. So that is what I wanted to point out with regard to this figure. And this slide basically summarizes what I was just talking about. So what we have plotted here is the 1D spectra, and as is the case with the 3D spectra, the energy spectrum function as in EF kappa, the Kolmogorov hypothesis do apply, right? Do apply, and they imply that this function here is a universal function of kappa 1 eta at sufficiently high Reynolds numbers and for kappa eta for kappa greater than kappa EI, as in the universal equilibrium range. So in this particular figure, you will see that for kappa eta greater than 0.1, all the data lie on a single curve. That is what you're seeing here. All the data lie on a single curve, isn't it? And the high Reynolds number data exhibit power law behavior for kappa eta less than 0.1. Less than 0.1. So that is in this range here. That is the energy containing range. So the data is actually consistent with E11 of kappa 1 divided by epsilon nu to the 5th to the 1/4, and that being a universal function for kappa 1 eta for kappa 1 eta greater than 0.1, isn't it? Which is where the universal equilibrium range starts. There are of course departures, but those departures are only in the energy containing range as mentioned here, where kappa 1 eta is less than 0.1, and the model spectrum represents the data very accurately, isn't it? Okay, now what is shown next is something even more interesting. What we are trying to do is, again, the same kind of spectra. Obviously, all that experimental data is not shown. It is still a 1D spectra though. It is scaled slightly differently. It is plotted against kappa 1 eta, that is for sure, but all that experimental data is not shown. Only two experimental data is shown, and this is what we call the compensated 1D spectra. It is not a scaled 1D, we don't call it a scaled 1D spectra, we call it a compensated 1D spectra because we have it as epsilon to the negative 2/3 kappa to the 5/3. Now where am I getting that from? I need to go back through my slides to see. Now look at this. I have epsilon to the 2/3 kappa to the minus 5/3 times FLKL F eta. So now if I take this to the other side, isn't it? If I take this epsilon to the 2/3 and kappa to the minus 5/3 to the other side, and so essentially I multiply that with, the epsilon to the 2/3, on the other side it becomes epsilon to the negative 2/3, and kappa to the minus 5/3 on the left hand side it becomes kappa to the 5/3, and I multiply that with the energy spectra. Then what am I left with? I am left with some universal constants. I am left with C, I am left with FLKL, and I am left with F eta K eta. So I do that. That's your compensated 1D spectra. And in addition to that, I'm doing one other thing. On the x-axis, I am plotting it on a linear scale. Okay, I'm plotting it on a linear scale, so it is kappa 1 eta. There are a few data sets shown here. One is the measurements of Comptibilo and Corzine from 1971 for grid turbulence at R lambda is equal to 60. So relatively low Reynolds number, still turbulent, but relatively low Reynolds number. Those are the triangles that you see in this symbol in the figure. And then the data from a turbulent boundary layer experiments of Sadogis for a turbulent boundary layer at R lambda approximately equal to 600. So that is pretty high. All right. Both of those cases are still turbulent, except one is at a relatively lower Reynolds number. So these are the only two data sets that are shown here. There are solid lines, in fact, there's a single solid line that represents the model spectrum at R lambda equal to 600. And then there is a dashed line, okay, and there is a dashed dotted line, which are the exponential spectrum and the power spectrum. What do I mean by that? So I have to go back here and look at, this is your exponential spectrum. And this is your power spectrum. Okay, so these two cases are shown here for the model spectrum. And as you can see, on a linear log scale, they are going to be lines, isn't it? This is your exponential spectrum and this is your power spectrum. All right. So that is just the exponential spectrum and power spectrum shown there, nothing else. The solid line is the model spectrum, so that contains the entire thing, right? The energy containing range, the inertial subrange, and the dissipation range. Whereas the exponential spectrum and the power spectrum, are only the dissipation range. But by doing this, by plotting this on a linear scale, earlier we had it plotted on a log scale, if you remember, this was on a log scale. Here, by plotting it on a linear scale, what we are trying to do is we are trying to enhance the dissipation range. We are trying to enhance the dissipation range. That's what we have done here. So your energy containing range is not really visible from this plot, right? It's there. In terms of the experimental results and the model spectrum, it is there. But by putting this on a linear scale and by compensating the 1D spectrum, what you have done is you have enhanced the dissipation range. And there's a reason for doing that. We can make some observations here. Okay. For one, you can see that the overlap of the data set onto the model spectrum, that is clear, right? That is clear. So then, and then if you look at the exponential spectrum and the power spectrum, they don't match as well. Okay. So here, what we are trying to do is, this is a compensated 1D spectra, a Kolmogorov scaling shown on a linear log plot. Again, to emphasize the dissipation range. You will see that for kappa 1 eta greater than 0.1, there is close agreement, right? There is close agreement between the model spectra and the experimental data set. for both Reynolds numbers. That's the interesting thing. For both R lambda is equal to 60 and R lambda is equal to 600, 10 times that Reynolds number, but still you see the universality of the high wave number spectra. Now, the straight line behavior is evident in this plot for kappa 1 eta greater than 0.3, which corresponds to the exponential decay of the spectrum. So you will see that beyond 0.3, right, and this is your dissipation range, you will see that straight line behavior because you have the exponential spectrum plotted on a log scale on the y-axis and a linear scale on the x-axis. Linear scale mainly to enhance the dissipation rate so that you can see it clearly. Here, when you looked at this plot, it was everything was together. So the dissipation range couldn't be emphasized as much, whereas here you're doing that. And the other observation is that we have shown here 1D spectra deduced from two alternative models for F eta K eta, which do not match as well as the model spectrum does. Okay, so that is what we are trying to show here. Understood? Now, here what I want to show is the dissipation spectra. The dissipation spectra is df kappa, which is integral 0 to infinity kappa nu kappa squared E of kappa d kappa. That is your dissipation spectra. We had shown this earlier, but I'm just writing this here again. So the dissipation spectra is nu kappa squared E of kappa d kappa from 0 to infinity. Now a couple of things are plotted here. I see two curves. The solid line is the dissipation spectra scaled. Okay, so that is just purely to non-dimensionalize it. So I have the dissipation spectra normalized with u eta cube. U eta is the Kolmogorov velocity and the cube of that. Okay, so I have the solid line showing here. That is your dissipation spectrum. Also shown here is a dashed line, which is the cumulative dissipation. So cumulative dissipation as defined as epsilon 0 kappa is 0 to kappa d kappa prime d kappa prime. So what does that mean? That is you are basically calculating the dissipation up until each wave number. Up until each wave number you are calculating the dissipation. So that's what it is, the cumulative dissipation. Now obviously because of the way it is calculated, you will get it to be equal to it, you will get it to be going to 1 eventually, and that is what is happening. This cumulative dissipation is normalized with epsilon, by the way. It is normalized with epsilon, which is the total dissipation. So d of kappa, I should say that it is 2 nu kappa squared E of kappa d kappa. There's a 2 factor there, but that doesn't matter. It is just a factor 2 in there. That is the way it is defined. And then I have the cumulative dissipation, which is again normalized with the total dissipation and is plotted. As you can see, it goes to 1 eventually. At high wave numbers, it goes to 1. The x-axis is shown on two different scales. One is this kappa eta, and in order to see how the scales vary, it is plotted against L over eta. So obviously L or kappa is 2 pi over L. So let me just erase this and write this again. We typically write kappa as 2 pi over L. So kappa is inversely proportional to L, of course, and that is why you have L decreasing here, whereas kappa is increasing here, isn't it? L is decreasing along the x-axis as you go from left to right, whereas kappa is increasing as you go from left to right, because L is inversely proportional to kappa. So that is the plot, right? This is the dissipation spectrum and the cumulative dissipation plotted here. Now all of this is calculated from the model spectrum analytically. You add the model spectrum derived at R lambda is equal to 600. These quantities are just calculated from those. a few numbers here, but I want to start with some observations of the spectrum. The peak of the dissipation spectrum occurs at kappa eta equals 0.26. What do I mean by that? The peak of the dissipation spectrum, that means dissipation is maximum, is at its peak at kappa eta equals 0.26, and kappa eta equals 0.26, which corresponds to L over eta approximately equal to 24, right? So that is the peak of the dissipation spectrum, 0.26 and 24. If you see here, that is 0.26 and 24. So that is where the dissipation is at its peak, at kappa eta equals 0.26, or L is equal to 24 eta, or L over eta is equal to 24. The centroid, all right, the centroid, as in the middle of the dissipation, occurs at kappa eta equals 0.34 and L over eta equals 18. So now let me look at that. The centroid, which is where the cumulative dissipation is 50% of the total dissipation, and that is this one right here. So that occurs here. This is the centroid, isn't it? 0.34 and 18, where epsilon k is half of epsilon, occurs at kappa eta equals 0.34 and L over eta equals 18. So let's say I marked that wrong. Okay, so this is, it's still 0.5, but it occurs here, 0.34 and then 18. It's slightly below the 20. So I'm not getting my scale right, but this is the peak. Let me just erase this, start over. So the peak of the dissipation spectrum, and I want to do dashed line here. So the peak of the dissipation spectrum is at 24. So again, that would be, it would be somewhere here. Okay, the centroid is corresponding to 0.5, isn't it? And that would be somewhere here at 18. All right, that would be the centroid. And as you can see, 90% of the dissipation is achieved at kappa eta equals 0.73 and L over eta equals 8.6. 90% of the dissipation. So that would be somewhere here. 90% of the dissipation would be here, close to this one. Onto the dashed line, then come down. So that would be here somewhere. Isn't it? So what we are trying to say is what? Okay, so the peak of the dissipation occurs at kappa eta equals 0.26. But look at where 10% of the dissipation goes and 90% of the dissipation goes. So that means, look at this range. 80% of the dissipation occurs between L over eta equals 8.6 and 6 to 3. Or essentially 8 to 60. 80% of the dissipation occurs there. The peak of the dissipation occurs at L over eta equals 24. That means 24 times the Kolmogorov scale. 80% of the dissipation occurs between 8 eta and 60 eta. Are you following me? So here you have the motions responsible for the bulk of the dissipation occurs between 8 and 60, isn't it? Occurs between 8 and 60, bulk of the dissipation, 80% of the dissipation, right? 0.1 to 0.9 is 80% of the dissipation. And it occurs between kappa eta equals 0.1 to kappa eta equals 0.73. That's what we are trying to say. So 0.1 to approximately 0.75. And between 8 and 60 eta, between 8 and 60 eta, much larger than the Kolmogorov scale. So what we are saying is that the the Kolmogorov hypothesis implies that the characteristic size, the dissipation motion scales with eta, and it need not be equal to eta. It scales with eta. So everything is consistent. So now we see where the demarcation length scale comes from. Remember, there was an LDI that we used, which we used it to be equal to 60 eta. And at that time I had said it's an arbitrary number that we'll come up with, but we will show that it actually makes sense. And as you can see, the bulk of the dissipation occurs between 8 and 60, approximately 8 and 60. So that is where the 60 comes from. LDI equals 60 eta comes from the fact that the dissipation, bulk of the dissipation is contained after this length scale. After meaning less than that length scale. That is how helpful this plotting the dissipation spectra was. We looked at the dissipation spectra and the cumulative dissipation in order to assess all of this. And because the cumulative dissipation showed basically that 10% of the dissipation to 90% of the dissipation, that is basically 80% of the dissipation, occurs between a certain range of length scales. So if you see here, it is 0.1 to 0.9. So essentially, most of this is the range that we are interested in, right? 8 to 60. 8 to 60. So 8 to 60 eta, 8 eta and 60 eta. That is where the most of the dissipation is contained in. That's what we are saying. So I hope this was clear. We will continue by looking at the next set of range like the inertial subrange and the energy containing range in the next class. Thank you.